Let's look at an example of a game where we can apply some of the ideas we've learned, like iterated removal of dominated strategies. We'll start with this partnership game. There are two partners, partner 1 and partner 2, and they each decide to make some effort level. So X would be partner 1's effort level, and Y is partner 2's effort level. The profit that their partnership yields is a function of both of their effort levels. So their profit, which I'll represent by pi, is a function of x and y. It's 4 times x plus y plus c times x times y, where c is some number between 0 and a quarter. So strictly greater than 0 and strictly less than 1/4. It's a measure of the complementarity between their effort levels. Since profit is actually a function of x and y, let's actually express pi as a function of x and y. So we'll write it as pi of xy is this. The game that's going to be played here is that the two partners have to simultaneously decide what the effort level is that they're going to make. Perhaps it's that they're working from home, or maybe they can't write a contract, and so they can't actually specify specifically and commit to some particular effort level. So it's as if they're making this choice simultaneously. So what are the strategies? The strategy set for each player is the space 0 to 4. So it's the interval 0 to 4. So each of them has to pick an effort level between 0 and 4. Effort isn't costless here. The cost to player 1 of expending effort level x is x squared, and the cost to partner 2 of expending effort level y is y squared. So the payoffs are going to be partner 1's payoff from the strategy profile x and y is half the profit minus the cost that he bears. So that's 2 times x plus y plus cxy minus x squared. Similarly, player 2's payoff from the strategy profile xy is half the profit minus the cost of expending effort y, which is y squared. We're going to use the idea of rationalizability here by first finding the best responses and then eliminating those strategies that are never a best response. So let's start with player 1 and figure out player 1's best response function. What is player 1's best response if player 2 is going to play the strategy y bar? Of course, we represent that by, to find the best response to y bar, player 1 has to find the effort level x that maximizes his payoff given that the other player is going to choose y bar. The first order condition is 2 plus 2c y bar minus 2x equals 0. So the optimal x is going to be 1 plus y bar times c. So the best response of player 1 to y bar is 1 plus c times y bar. Similar reasoning will tell us that the best response of player 2 to player 1 choosing some level x bar is 1 plus c times x bar. Technically, I should have written here that BR1 of y bar is actually the set containing only 1 plus c y bar, because the best response is always a set of strategies for player I. So player I's best response to some strategy played by the opponent is some set of strategies that are best responses. But whenever we have that set is a singleton, so there's always a unique best response in this particular game, then we just take a shortcut and we just write it this way. We just write that 1 plus c y bar is the best response rather than saying the best response being the set containing the only element 1 plus c y bar. The best response of player 1 to a choice of y by player 2 is, remember, 1 plus c times y. And the best response of player 2 to a choice of x by player 1 is 1 plus c times x. So these are both straight lines with a slope of c. So let's look at the graph of the best response of player 1. the lowest strategy that player 1 can have as a best response is 1. So the lowest value that this can take is 1 when y is 0, and y goes between 0 and 4. So this is somewhere between 1 and 1 plus 4c. So when we graph that, we see exactly that. X takes values only between 1 and 1 plus 4c. So these things are never best responses. So anything outside of that set is never a best response for player 1. Similar reasoning tells us that the best responses for player 2 are only between 1 and 1 plus 4c. So none of these are best responses. After one round of elimination, we're left with, for each player, I, the surviving strategies that can be a best response are those strategies between 1 and 1 plus 4c. So that's round 1 of removing strategies that are never a best response. For the next round, we'll draw a new picture and we'll just zoom in and keep only those strategies that survived. Now on each axis, we only need to mark the strategies available to the player after we've removed the strategies that are never a best response. So the only strategies that we need to put on each axis are those strategies between 1 and 1 plus 4c. So the best responses for player 1 to strategies of player 2 between 1 and 1 plus 4c are between 1 plus c. The best response to y equals 1 is just 1 plus c. The best response to y equals 1 plus 4c is 1 plus c times 1 plus 4c. So these strategies, again, just like before, these strategies are not a best response. Similarly, we get that these strategies are not a best response. So the strategies that remain after we do a second round of elimination for player I are the strategies between 1 plus c and 1 plus c times 1 plus 4c. In general, if we've done this for some rounds, after the round k minus 1, we would have some interval rk minus 1 for player I. So we would have some lower bound and some upper bound on these strategies that player I could play. What you'll find is that when you do the kth round, the interval rk is just the best response for I to the lower bound for player j to the best response for I to the upper bound for j. If we keep going, these intervals are going to keep getting smaller and smaller, but we'll be able to shrink these infinitely many times. We can take the limit, and those are basically going to be the single point where these two best responses cross. So the only rationalizable strategy profile is where both players play 1 over 1 minus c. And that's the point where the best responses cross. So on the basis of solely common knowledge of rationality, we can conclude that the outcome of this game is that both players are going to choose the effort level 1 over 1 minus c. So what profit does that lead to for the two players? What are the payoffs that they're both going to get? The profit is going to be 4 times x, which is 1 over 1 minus c, plus y, which is 1 over 1 minus c, plus c times x times y. Since x and y are both 1 over 1 minus c, that's c over 1 minus c squared. We could simplify that and we would get 8 minus 4c divided by 1 minus c squared. So if we split the profit between the two partners, each partner's share of the profit is 4 minus 2c divided by 1 minus c squared. The cost that they each suffer is 1 over 1 minus c squared. So the payoff to each partner is just the profit that they get, the share of their profit, so 4 minus 2c divided by 1 minus c squared, minus the cost that they suffer, which is 1 over 1 minus c squared. And that's just 3 minus 2c divided by 1 minus c squared. Is this an efficient outcome? Ideally, what you would do is to have each of the partners pick their effort level to maximize the total profit net of the costs that they incur, and then distribute the gains over the cost between the two. So can we do better than these utilities for the two players if we made the decision jointly? Well, the joint decision would solve the following problem. And the first order condition would be for x and for y. If we solve those, we'd get the following optimal x and y. Each of these partners in the optimal outcome are going to engage an effort level 2 over 1 minus 2c. And of course, 2 over 1 minus 2c is higher than 1 over 1 minus c. It's a smaller denominator, bigger numerator. So each of these individuals is going to put in a greater amount of effort at the optimum than they would in the only surviving rationalizable strategy. So what we see here is that the effort levels that arise in the only plausible outcome when the two partners make their decisions independently are lower than the optimal levels of effort. So this is another example where we see that the predicted non-cooperative outcome is inefficient. So individual incentives don't necessarily lead to the best outcome for everyone. We see this also happen in the Prisoner's Dilemma game in a more obvious way.